Before starting with my presentation, I would like to say many thanks to my supervisor, Mr. Horaud and Nicola Conci, and my co-advisor, Radu and Silva. The title of my thesis is ViProT, which stands for a visual probabilistic model for moving interpoint cluster tracking. This thesis is the result of my master project that I took during my internship at perception team at INRIA Grenoble, Rhone-Alpes. The main goal of my master project was to propose and develop a method able to combine the clustering of visual observations and the tracking of localized objects by means of a probabilistic graphical model. This method should be embedded in a wider approach for audiovisual perception in the context of human-robot interaction, which perception team has been investigating. So I would like to start explaining what object tracking is, and object tracking is the estimation of the trajectory of an object over time by locating its position in every frame of the video. Here there is an example of multiple object tracking in which there are three people that are moving around, and we also depicted the trajectory of each person. Dealing with multiple object tracking is a complex task because many other issues arise. For example, we need to estimate how many objects are in each frame of the video, to estimate the object-to-object association between two successive frames. If an object is still, we need to understand if an object is still in the video or it exits in a previous frame, or, for example, a new object appears in the video. And we also need to deal with crossing objects. Strictly related to object tracking is the object representation, because we want to know what we want to track. So we can represent an object based on its shape, its texture, or its appearance. Here there are some examples of shape-based object representation. So, for example, single point, multiple interest points, or elliptical patch. Multiple object tracking is a widely investigated problem in the computer vision community, and several approaches have been proposed until now. For instance, near single standard filter, multiple hypothesis breakers, and probability density filter. But none of them are able to solve all the issues that we saw previously at the same time. And all these techniques usually are suitable for specific application or in specific context. In our case, because we are dealing with a robot, we assume that relevant objects are in a distance of 3-5 meters far from the cameras embedded into the head of the robot. So, given an input image like this that we are coding with our robot, we use Harris point detector to find a lot of points in each frame of our video, and taking into account a sequence of these frames, we filter these points based on motion. That means that we preserve only those points that are not fixed in successive frames. In the end, what remains is this set of observation without the image behind, and as you can see, we are not able to distinguish the objects anymore. This will be the input of our method. So we propose this probabilistic graphical model where we denote with F the set of our observation. And we need to estimate the assignment, the observation to object assignment, and the source position. So we assume that this set of observation is changing over time, and each observation follows a normal distribution. Z is a hidden variable that assigns each observation FTK to sources, and PTN is a hidden temporal variable which denotes the position of the end source at any time. We suppose that each source follows again a zero-order Gaussian model, which is linearly in two successive frames. We also suppose that the number of objects is fixed and an a priori information. Starting from the described graphical model, we derive the well-known iterative expectation maximization algorithm for this specific graphical model, and we wrote the expected complete data log like Q, here denoted by the Q function. For this, in DM algorithm, we compute the probability inside the logarithm for the expectation step, And during the maximization step, we estimate the model parameter by maximizing the Q function. All the derivation can be found directly in the written thesis, but I would like to focus on one important thing. The expectation step of this graphical model has not a tractable closed form solution, computationally tractable closed form solution. Indeed, the assignment variable z makes the expectation step combinatorial and therefore computationally too expensive. To overcome the problem, we use the variational approach which allows to factorize the expectation step, and we chose the exponential family as an approximation. Besides, we add some extension to our method by first of all modeling outliers, which are observations that are not generated by our objects but by other sources, and we assign this observation to a specific class, the outlier class. And we also model the velocity as another hidden temporal variable, which allows to make the trajectory estimation more precise. So we made some experiments both with synthetic data and the real video. In this case, I report an example of a scenario with 3 objects that are moving in a certain area and they are crossing each other. We estimate the trajectory with a method that takes into account outliers and velocity. And as you can see, the trajectory estimated are close to the ground truth. To evaluate this scenario, we use the root mean square error between the estimated position and the ground truth position for each object and for each time step. We made a comparison among methods, as you can see on the left, with a combination of the different extensions. In the table, I report the mean and the variance of this matrix, and as you can notice that the adding of our extension can improve the performances of our model. Here there are some demos. As you can see, our algorithm is working well because we are able to cluster the observation properly above over the people, and we are able also to follow the motion of these people. I would like to show you another example. In this video, the scenario is more complex because these 3 people are moving around and they are crossing each other. Here something strange happens. As you can see, the clustering is not properly above the people, and also we have a switching problem between the estimation and the ground truth. So this is a well-known problem in computer vision and is called occlusion. And occlusion is an event that occurs when 2 objects overlap, and one is partially visible or not visible at all. And this is due to the projection of the 3D world in a 2D image. To evaluate these real videos, we use other 2 metrics. One is identification, which measures a spatial temporal relation between estimated objects and ground truth objects, evaluating the constant tracking of an object by a particular estimate over time. And we use an identity state, which is a binomial variable, to say that to see if the correspondence between the ground truth and the estimated is correct or not. On the other hand, we use another metric, the object coverage accuracy, which is the ratio between the number of frames that each ground truth is successfully covered by at most 1 estimate and the total number of frames. An object is successfully covered when the central point of one estimation is inside the annotated rectangular box of the associated ground truth. Just to be more clear, here an example of a video. On the top left, you can see the initial frame of the video, where the estimations are correctly associated to the ground truth. On the right, you can see a successive frame where the identification, the coverage are correct, below the error. So on the left, there is the coverage error, where the central point of the blue elliptical patch is outside the blue rectangular box, which is the ground truth. And on the right, you can see a totally wrong identification between the estimates and the ground truth. So the results of these two metrics are perfect for the first two videos, but in the third video, as you can see, the performances are dropping down, and as we expected, due to the occlusion, because we didn't model the occlusion in our initial method. And in this case, the results are related to the method of taking into account outliers and velocity, because there are no relevant improvements among these methods. In conclusion, we propose a probabilistic graphical model, and we derive the expectation maximization of a method that is able to estimate the model parameter of this expectation maximization algorithm, is able to estimate the observation to object assignment, and is able to track multiple objects. And this is working in a context of multiple longitudinal objects when these objects are 3-5 meters far from the camera embedded into the robot. For sure, there are some limitations. One could be our assumption of fixed number of objects, because usually tracking requires that your algorithm should be able to deal with a variable number of objects, but in any case, it could work for specific reasons. As we saw, occlusion is another issue, and in the end, also our dorsal assumption could be an issue, because in real videos, the generated observation could not belong a Gaussian. So we can think, for example, to another distribution. So in the end, in conclusion, finally, for the future, we are thinking to embed depth, motion, and color information into interest points in order to solve the occlusion problem, or to make the clustering part more robust. Indeed, if you have two interest points that are moving in two different directions, you can assign those points to a different clusters. We would like to make our method real time, because for the moment we are dealing with already recorded videos, and real time is another requirement for tracking algorithms. And in the end, we would like to add a birth depth process in order to deal with the entry or exiting of objects in our videos. So thank you for your attention, and if you have any questions.
Thank you.
Questions?
Give us a little show that people that are moving very slowly, normal velocity.
In this case, the video are slowing down.
Okay.
Because the normal frame rate of the video are 25.
Okay.
So
It's only a visualization
yes.
problem.
Yes.
Okay. I'm not sure if in your case in the video, so this is the right moment, to the comparison with the similar model of the daily work, so did you compare that in some way the experience with?
No idea. No.
And the other question is about the technical content. I saw in your case a lot of technical content. What is your contribution on that? Do you seem to report equations from others, or this model?
My contribution?
Your contribution.
My contribution, I propose this graphical model. Yeah. I derive mathematically the expectation optimization algorithm. I implemented the expectation optimization algorithm, yeah. And I annotate some real videos. I generate the scenarios, and I test all this stuff, and by choosing also the metrics in order to test.
Yeah, there is an entire section of technical content. Equations, over equations. This is your contribution?
Yes, I derive this part.
Why you need so much technical work? This is called technical content. Why you need so much? Can you summarize it, because we cannot read it in few minutes? So what was the main requirement for developing all these equations? So why you need all these parts?
We try to propose a new model for the tracking, which should be able to combine the clustering part, because at INRIA there is already a work that they are working on the clustering of audiovisual observation, but they hadn't any algorithm to able to track these localized sources over time.